Welcome to the deep dive. Today we're tackling something that's pretty crucial for anyone stepping into a senior software engineering role, especially when you're, navigating those technical interviews. We're going to dissect a common design pattern that offers a really smart way to handle complexity in your code.
Absolutely. We're going to explore how structuring your thinking around the different states an object can inhabit can lead to code that's not only cleaner, but also, frankly, significantly easier to maintain and evolve. It's a fundamental concept. And yeah, a solid understanding of it can really set you apart when discussing design choices during an interview.
Okay, let's dive right in then. Think about a common scenario. You've got an object in your system. Maybe it's managing, a file download. That download could be in various states. Perhaps it's just started, it's currently in progress, it's finished, or maybe it's failed. Now, the actions you can perform on that download and the results of those actions, well, they'll be completely different depending on which state it's in, right?
That's spot on. A very basic way, maybe the naive way to handle this would be to just pepper your code with conditional logic. Imagine the methods of our download manager object: start, pause, resume, get progress. Inside each of these, you might find a whole cascade of if-else statements, or maybe a big switch block, just checking the current state to determine what should happen next.
Right. And to really illustrate the challenges here, let's think about a classic example, the Gumball Machine. Envision a simple implementation where we represent the states with integers, maybe like 0 for when it's out of gumballs, 1 if it's waiting for a quarter, 2 if a quarter has been inserted, and maybe 3 if it just dispensed a gumball.
Exactly. And then within each operation, like insert quarter, eject quarter, and dispense, you'd have a series of checks against that state variable. So for instance, if you try to insert a quarter and the machine is already in the has quarter state, you'd maybe output a message saying can't accept another one. But if it's in the no quarter state, you'd update the state to has quarter and perhaps register that the quarter has been received.
Now, here's where things can get, well, really tricky. What happens when the requirements change? Let's say the Gumball Machine company decides to introduce a special winner state where there's like a small chance of getting 2 gumballs instead of 1. In our initial approach, the one with all the integers and if statements, we'd have to go back and modify every single method to include a new conditional check for this winner state.
And that's a critical drawback. That kind of approach, it starts to violate a really key principle of good software design.
Yeah.
The open-close principle. You want your code to be open for extension, meaning you can add new functionality, but ideally without having to modify the existing working code. This integer-based state management, it just leads to code that becomes increasingly complex and, frankly, difficult to reason about. Plus, the transitions between states become sort of implicit and scattered all over the place within those conditional checks, making it really hard to get a clear picture of the machine's actual life cycle.
So what's a more elegant, more maintainable way to tackle this kind of state-dependent behavior?
Okay, so that's where the state design pattern comes in. It provides a much more structured and object-oriented solution. The fundamental idea is to represent each distinct state as its own separate class. So instead of having one big object with a state variable and a bunch of conditional logic, you have a collection of objects, each one dedicated to managing the behavior associated with a specific state.
Okay, so we're essentially taking those integer representations, those numbers, and turning them into actual concrete classes. What are the main components or like the players in this pattern?
Yeah, there are typically 3 core participants. First, you have the context. This is the object whose behavior changes depending on its internal state. Think back to our examples: the TCP connection, the Gumball machine, or even a drawing controller in a graphics app. The context keeps a reference to the current state object, and it delegates any state-specific requests to that object.
Right, so the context knows what state it's in, but it doesn't necessarily need to know the nitty-gritty details of how each state operates.
Precisely. Second, you have the state itself. This is usually defined as an interface or maybe an abstract class. It establishes a common contract, defining the set of methods that all the concrete state classes must implement. These methods correspond to the actions that can be performed on the context.
Like open or close for a connection.
Exactly. For a TCT state, you might have open, close, acknowledge. For a drawing tool state, it could be methods like handle mouse press, handle mouse release, handle character. Basically, it defines what actions any state needs to be able to handle.
Okay, so it's like a blueprint that all the specific state behaviors have to follow. Makes sense.
Exactly right. And finally, you have the concrete states. These are the actual classes that implement the state interface or extend the abstract class. Each concrete state represents one particular state of the context and provides its own specific implementation for those methods declared back in the state interface.
Oh, okay.
So for our TCP connection example, we'd have classes like TCP established, TCP closed, and TCP listen. Each one would handle open, close, and acknowledge in a way that's relevant only to that specific connection state. They define how those actions are performed when the connection is, say, established versus when it's closed. Similarly, for drawing tools, you might have creation tool, selection tool, text tool classes, each behaving differently.
Okay, I think the structure is becoming clearer now, but how does this actually translate into the object's behavior changing dynamically? How does the delegation work?
Yeah, the key mechanism here is delegation. When a client makes a call to a method on the context, let's say Gumball Machine.InsertQuarter, the Gumball Machine object itself doesn't actually contain the logic for what happens when a quarter is inserted.
Okay.
Instead, it just forwards or delegates that call to the InsertQuarter method of the current state object that it's holding a reference to.
So if the Gumball machine is currently holding a no quarter state object, the insert quarter method defined inside the no quarter state class gets executed.
Exactly.
And if the machine then transitions, maybe is setting its current state to a has quarter state object, then any subsequent calls to insert quarter on the Gumball machine will be handled by the implementation inside the has quarter state class instead.
Precisely. Each concrete state class encapsulates the specific behavior for all the defined actions, but only for when the context is in that particular state. That's how the context's overall behavior adapts based on its current internal state. And the crucial advantage, really, is that the context itself remains relatively simple. It's mostly just responsible for knowing its current state object and delegating the requests. It doesn't get bogged down in all that complex conditional logic.
That separation seems really powerful.
It is. It makes the code not only easier to read, but also significantly simplifies debugging because, if there's a bug related to the established state, you know exactly which class to look at. TCP established.
Let's maybe solidify this with a couple more examples, maybe ones more common in software systems. You mentioned TCP connections earlier. How would the state pattern typically be applied there?
Sure. So imagine you have a TCP connection class. It would have a field, maybe called current state, to hold a reference to a TCP state object. This TCP state might be an abstract class with methods like open, close, and acknowledge. Then you'd have your concrete state classes. TCP established, TCP listen, TCP closed. When you call, say, open on the TCP connection object, it just delegates that call to the open method of whatever object current state is pointing to.
Okay.
So in the TCP close state, the open method might kick off the TCP handshake process. If that's successful, it would then transition the TCP connection state by changing the current state reference to point to maybe a shared instance of TCP established.
And what if you call open when it's already established?
Good question. In the TCP established state's open method, it might just do nothing. It's a no-op, or perhaps it could throw an exception, because trying to open an already open connection isn't really a valid operation in that state.
That makes a lot of sense. And thinking about user interfaces, you also mentioned drawing application tools. How does the state pattern fit in there?
Right. In that kind of scenario, the drawing controller, or maybe canvas view, would act as the context. You'd have an abstract tool state defining methods like handle mouse press, handle mouse release, maybe handle character for text tools.
Got it.
When the user selects the creation tool from a toolbar, the drawing controller would set its current state to hold an instance of the creation tool class. Then, when the user clicks the mouse on the canvas, the drawing controller just delegates the handle mouse press call to that creation tool object.
And that object would then start drawing shape.
Exactly. It would contain the logic for initiating the drawing of a new shape. Then, if the user switches to the selection tool, the drawing controller updates its current state to be an instance of the selection tool class. Now, any subsequent mouse presses are handled by the selection tool object, which would implement logic for, say, selecting existing shapes on the canvas.
Okay, great. Let's circle back to our gumball machine for just a moment. How does applying the state pattern fundamentally change our initial sort of cumbersome implementation with the integers?
Okay, so in the refactored Gumball machine, the Gumball machine class becomes the context. We define a state interface like we discussed with those familiar methods.
Yeah.
Insert quarter, eject quarter, turn crank,
Yep.
and dispense. Then we create our concrete state classes: no quarter state, has quarter state, sold state, and sold out state. The Gumball machine just holds a reference, let's call it current state, pointing to one of these objects. When you call Gumball machine.insert quarter, it simply does current state.insert quarter.
So inside the no quarter state class, its insert quarter method would contain the logic for what happens, then maybe it updates the display, and crucially, it tells the Gumball machine context to transition its state, probably by calling something like Gumball machine.setState, Gumball machine.get quarter state.
Exactly. The state object itself often drives the transition. And similarly, within the quarter state class, its insert quarter method would implement the behavior for trying to insert another quarter when one is already there. Maybe just displays an error message, and importantly, doesn't change the state. It remains in quarter state.
Okay, and now going back to adding that winner state, how does that look with the pattern?
That becomes much cleaner, much more isolated. First, you create a new winner state class. It implements the state interface, just like the others. Its unique behavior would likely be in the dispense method, where it releases 2 gumballs and then probably transitions the machine back to no quarter state, assuming it's not sold out.
Okay.
Now, the only other place you need to make a change is inside the turn crank method of the existing quarter state class. In there, you add the logic to check for the 10% chance. If the check passes, you tell the Gumball machine to transition to the new winner state instance. If it fails, you tell it to transition to the regular sold state instance, just like before.
So we didn't have to touch no quarter state, sold out state, or make any significant changes to the core Gumball machine context logic itself, just added the new state and modified the one state that leads into it.
Exactly. That really showcases how the state pattern properly supports the open-close principle in practice. The system becomes much more resilient to future changes and extensions.
That definitely highlights the extensibility this pattern provides.
Right.
So beyond that specific benefit, what are the main sort of core advantages we get by adopting the state pattern?
Yeah, there are several pretty significant advantages. First, and maybe most importantly, it localizes state-specific behavior. All the code related to a particular state, how it handles insert quarter, turn crank, etc., is neatly encapsulated within its own dedicated class. This makes it far easier to understand, reason about, and, importantly, modify that behavior in isolation later on.
Right, no more hunting through giant Eiffels blocks.
Exactly. Second, it makes state transitions explicit. Instead of state changes being implicitly managed within that tangle of conditional logic, the transitions are clearly defined, usually within the state classes themselves. Often, a state object decides which state the context should move to next based on the action performed. Third, as we've already touched on quite a bit, it strongly supports the open-close principle. You can introduce completely new states into the system simply by creating new concrete state classes that implement the state interface. You generally don't need to modify any of the existing state classes or the context itself in major ways. This is just crucial for long-term maintainability, especially in systems that evolve over time.
And it does effectively get rid of those sprawling, hard-to-manage conditional blocks we started with, right?
Absolutely. By delegating the actual behavior to these separate state objects, you dramatically reduce the number of conditional statements within the context class itself. This leads directly to a significant improvement in code organization and overall maintainability. Things are just tidier. And here's an interesting sort of optimization or related idea. If your concrete state objects don't need to maintain any internal instance-specific data, meaning they're essentially stateless themselves, they can potentially be shared across multiple instances of the context.
Oh, like having just one no quarter state object used by all Gumball machines?
Precisely. This is a variation often combined with the flyweight pattern. If you have, say, thousands of Gumball machines, sharing those state objects can lead to significant savings in memory usage because you're not creating new state objects for every single machine.
That's a great point about efficiency, especially at scale. Now, are there any practical considerations or maybe potential drawbacks to keep in mind when implementing the state pattern? It sounds great, but are there trade-offs?
Yes, absolutely. There are always trade-offs in design. There are a few important implementation considerations. One key question you have to decide is who should be responsible for initiating the state transition?
Right. Does the context decide or does the state decide?
Exactly. Should the context object itself contain logic to decide, okay, after this action, I should now be in that state? Or should the concrete state classes determine the next state based on the outcome of their operations? Generally, it's often considered more flexible and more in line with the pattern's intent to allow the state subclasses themselves to trigger the transitions. This keeps the transition logic close to the behavior of each state.
But does that create dependencies? Like, does no quarter state need to know about has quarter state?
It can, yes. That's the
Oops.
potential downside. It can introduce dependencies between different concrete state classes. A common technique to mitigate this is for the state classes to not directly instantiate the next state, but rather to call setter methods provided by the context. For example, context.setState, context.get has quarter state. The context might provide getter methods for accessing shared state instances or necessary information, reducing direct coupling between the concrete states.
Okay, that makes sense. You mentioned the open-close principle being a major benefit, but are there situations where maybe the state pattern might actually feel like more complexity, just in terms of the sheer number of classes you end up creating?
That's a totally valid point. For a system with a really small and crucially fixed number of very simple states and transitions, the added structure of the state pattern, having an interface, multiple concrete classes, it might feel a bit like overkill initially.
Right, like if you only have two states, maybe an if statement is fine.
You might be, yeah. In such simple cases, a more basic approach using maybe just enums and a few straightforward conditional statements could suffice and might even be easier to grasp at first glance. However, the real power and benefit of the state pattern become much more apparent as the number of states grows, or as the complexity of the behavior within each state, or the logic governing the transitions increases.
So it scales better.
It definitely scales better. What might seem like a small increase in the number of classes up front often pays off significantly down the line in terms of improved organization, much better maintainability, and that crucial extensibility as the system inevitably evolves. You're essentially trading a potentially slightly larger initial code base for one that is much, much easier to understand, test, and modify safely in the long run.
Okay. Earlier, we briefly touched upon alternative ways to manage state, like using tables. Could you maybe elaborate on that comparison a bit more?
Sure. Yeah, another approach you might encounter, especially in older systems or certain domains, is using state transition tables. In this model, you essentially define a table, maybe a 2D array or a map, where the rows might represent the current state, the columns represent possible inputs or events, and the cells within the table specify what the next state should be, and potentially also identify an action or function to execute.
Hmm.
While this approach can be effective, especially for systems with very well-defined and relatively static state transitions, it can become less manageable and, frankly, harder to understand as the complexity of the actual state behavior increases. The state pattern really excels at modeling the behavior associated with each state directly within its class, making it, I think, more intuitive for complex actions.
So the table focuses more on the transitions, while the state pattern focuses more on the behavior within the state.
That's a good way to put it. Transition tables primarily map inputs to next states. You often still need separate logic somewhere else to actually implement the specific behaviors or actions that need to happen in a state or during a transition. Furthermore, when you need to add new behavior associated with an existing state using a table-based approach, you typically end up modifying the code that interprets the table or the action functions. With the state pattern, you'd ideally just modify or extend the corresponding state class, which generally aligns better with object-oriented principles like encapsulation and the open-closed principle.
Gotcha. And what about the life cycle of the state objects themselves? You mentioned they could be shared. When are they typically created and managed?
Right, there are a couple of common strategies there. One approach is to create instances of all the necessary concrete state classes up front, maybe when the context object itself is created. These could be stored as fields within the context. The context then simply switches its current state reference between these pre-existing, often shared state objects as its state changes.
Okay, so create them all at the start.
Yeah. This can be good for performance, especially if state transitions happen really frequently, because it avoids the overhead of creating new objects during every transition. The other main approach is to create state objects on demand, only when the context actually needs to enter that particular state for the first time.
Lazy loading, kinda.
Sort of, yeah. This can be more memory efficient if you have a very large number of states, especially if some of those states might not actually be used very often during the typical lifetime of a context object. The choice between these strategies, create upfront or create on demand, often depends on the specific requirements, the frequency of transitions, and the performance characteristics you're aiming for in your application.
Now, something you see mentioned a lot is that the strut pattern bears a strong structural similarity to another well-known pattern, the strategy pattern.
Hmm.
Could you maybe shed some light on the relationship and, more importantly, the key differences between them? Because they can look really similar diagrammatically.
That's an excellent observation, and it's a common point of confusion. In fact, if you just look at their basic UML class diagrams, context holding a reference to an abstract type, with multiple concrete implementations, they can appear remarkably similar, almost identical sometimes. However, the crucial distinction lies in their intent, the fundamental problem they are trying to solve. The state pattern is primarily about controlling an object's behavior based on changes in its internal state. These state changes typically occur over the lifetime of the object, often happening somewhat automatically as a result of actions performed on the object, and frequently without the direct knowledge or explicit intervention of the client using the object.
Okay, so state is about internal changes driving behavior. What about strategy?
The strategy pattern, on the other hand, is about encapsulating a family of interchangeable algorithms or behaviors. The key difference is that the client usually chooses and explicitly provides the specific strategy object that the context should use to perform a particular task. Think of strategy as a way to easily switch between different algorithms for doing something like different sorting algorithms or different compression methods. State is more about an object's inherent behavior changing as it moves through different stages or conditions of its own existence.
So let me see if I've got this. With the strategy pattern, the client is making a conscious decision about how something should be done by actively selecting and plugging in a specific strategy algorithm.
Correct.
Whereas with the state pattern, it's more about the object's own internal condition dictating what it can currently do and how it behaves. And this change in behavior might happen somewhat transparently to the client, just as a consequence of using the object.
That's a perfect way to summarize it. You can think of strategy as achieving behavioral variation through composition. You change the algorithm by composing the context with a different client-provided strategy object. State, on the other hand, is more about behavioral variation based on internal circumstances. The object's behavior changes because its own internal state has changed, often as a result of its own methods being called.
This has been a really insightful exploration, bringing it back then to the perspective of someone preparing for those senior technical interviews. How valuable is really understanding the state pattern in that specific context?
Oh, understanding the state pattern is incredibly valuable. It demonstrates a really solid grasp of fundamental object-oriented design principles. It shows that you can think beyond just basic procedural logic or simple conditional checks to address complex behavioral requirements in a way that's well-structured, maintainable, and extensible.
So it signals good design sense.
Absolutely.
Hmm.
Being able to clearly articulate the problem that the state pattern solves, managing state-dependent behavior, cleanly explain its key components like context, state, concrete states, and its benefits like supporting open-closed, and maybe even identify scenarios where it would be an appropriate design choice. That can significantly impress interviewers. It signals that you understand how to design software that is not just functional, but also robust, extensible, and easy for a team to reason about and maintain over time, all absolutely critical qualities they look for in a senior-level engineer.
So, if an interviewer presents a design problem, maybe something involving, say, an order processing system or a document editor, where an object clearly needs to behave differently based on its internal conditions, like order placed, order shipped, document unsaved, document saved, thinking about the state pattern and being able to discuss its potential application, its pros and cons in that context, would be a strong indicator of your design skills.
Absolutely. It shows that you're familiar with established, proven design patterns, and importantly, that you can apply them thoughtfully to create elegant and maintainable solutions. It shows you're not just going to resort to ad hoc methods or create those overly complex, hard-maintained conditional logic structures that we talked about initially.
All right, let's start to bring this deep dive to a close then. For our listeners who are, actively preparing for their next technical interview, what are the absolute key takeaways regarding the state pattern they should really lock in?
Okay, I think the most important things to remember are, 1, the state pattern provides a clean, object-oriented way to manage state-dependent behavior by encapsulating each distinct state as its own separate class. 2, The context object maintains a reference to its current state object and simply delegates state-specific requests to it.
Right, delegation is key.
Delegation is key. 3, this approach leads to code that is way more modular, much easier to extend with new states later on, thanks to the open-close principle, and it avoids the complexity and maintainability issues of large, monolithic conditional blocks. And finally, 4, it makes the transitions between states more explicit and generally contributes to better overall code organization and long-term maintainability.
So, summed up, instead of one giant class trying to juggle multiple personalities based on a tangled web of if statements, you break it down. You have a collection of focus, single responsibility state classes, each expert in the behaviors relevant only to that specific state.
Precisely. It's really about making the concept of state a first-class citizen in your design, treating it as a core architectural element, which ultimately leads to more robust, adaptable, and understandable software.
Well, this has been a fantastic deep dive into the state pattern. Really helpful stuff. For our listeners, here's maybe a final thought to consider as you continue your interview preparation. Think about systems you've worked on, or perhaps even complex systems you've just used or studied, maybe in previous projects, or even in open source software you admire. Can you identify any areas where the state pattern might have already been applied, perhaps subtly? Or maybe more interestingly, can you spot areas where its application could have significantly simplified the design and improved maintainability compared to how it was actually built?
Yeah, that's a great exercise.
Yeah. And think about what might have been some of the trade-offs involved in choosing this pattern over other potential approaches in those specific situations. Reflecting on these real-world or near-real-world scenarios will not only solidify your understanding of the state pattern itself, but will also equip you with valuable, concrete insights and examples to share during your technical interviews, showing you can apply these concepts practically.
Absolutely. Consider how you might articulate the benefits, and maybe even the potential costs, of using the state pattern in the context of a specific design problem you might be asked to solve during an interview. Being able to discuss design patterns not just abstractly, but with concrete examples and a clear understanding of their trade-offs is a real key differentiator for senior engineering candidates. It shows practical wisdom, not just book knowledge.